little intro. Hello, this is Colin, the Mark 11 Mechanical Technical Director. This video's regarding engineering drawings and getting a bit of an intro into GD&T. Um, so yeah. Overall intro, I'm gonna preface this with I am not like industry expert on all these topics. A lot of my experience is just from like working on drawings within the club and learning a bit from like internships. Um, but there's definitely a lot more knowledge. There's a whole rabbit hole of going into different engineering drawings standards and GD&T, which I'll talk about in a bit. There's a lot of like resources online where you can learn a lot more. There's a bunch of textbooks and stuff. If you are interested in like learning a bit more about this, feel free to come up and talk to me. I can point you towards some stuff that's like pretty useful. Yeah, this is like just to sort of get you to the base level where you can actually like make some drawings for your parts on the car this year, or like at least be aware of what's going on if you're like working at a company and they're like asking you to do this, just so you're just generally in the know. Drawings are a pretty important part of like the engineering process, especially in industry. Um, so yeah, after this, we'll do a bit of a shared example, just showing you like the SolidWorks UI, and like how you might actually apply some of the topics, because it's like pretty information dense. This one might be a bit longer than the other one, but so jumping into engineering drawings, like what is it? It's like a set of like precise documents that are made to really communicate how a part's supposed to be like assembled or inspected. Um, it should be like the main point of communication for any part. You guys might be a little more used to actually using CAD for like communicating parts, but a lot of times, um, what you'll see is like it's pretty hard to get a lot of information from there, right? If I ask you like, hey, can you give me this info about your part? You have to open up the CAD, you're like grabbing the measure tool and you're like clicking different points. You misclick a point, you restart. It takes us 5 minutes to get one dimension. So the point of this is to really like clear up that like route of communication. It should be super simple for someone to look at your drawing and really understand in like a simple way like what your part does, or maybe not what it does. They're not always allowed to know that, right? Especially in industry. Some stuff's like classified or like you need clearance for. So they just need all the necessary info, like what makes a part acceptable. Yeah, it can contain any like amount of detail depending on what you're actually using it for. You might be making a very simple part where it's just basic dimensions. I'm telling you, this is roughly like 3 inches long, right? Something like that. You can add little notes for something like, hey, like when you're using this, like use this specific drill bit, or like tape this first before you assemble it, right? Any note that might be useful for instructing like someone else to help you like build something. Um, yeah, it's a really scalable system. You can use drawings for anything. Like you can use it for these simple clevises here that we use in the wheel system, or you can use it for a lot more of a complicated part like the uprights. You could even go all the way to assembly level drawings where you'll have like a million parts in there and you're showing how they mate together and the whole assembly process. So drawings are pretty flexible. You can use them for a lot of different purposes. Why does it matter? One big thing is it really enables your quality control. Um, this is something where like it's not as like explicitly like taught or like used as often, especially when you're in school. Your any like lab won't have you make drawings really, for like any project, or at least that I know of. Um, or for clubs, it might be pretty wishy-washy where they're like, hey, just make it off of CAD. I don't feel like making a drawing. And you just make it as close as you can. Sometimes that's good enough. Um, but like as you move into industry, right, and you're working with like parts that like cost a lot of money, that's where you might start to see it a lot more. Another thing that's like will vary a bit in industry is that the machinist or like the tech who's actually working on your part is rarely the designer of the part. So in clubs and stuff, we're used to like doing everything ourselves, right? We're like getting hands-on in the machine shop. Um, and we're also the ones like assembling our products, right? We see it from like cradle to grave almost. Um, But a lot of times, work is split up. It's like maybe not like efficient for someone to be doing design, manufacturing, and assembly when they can get like specialists, like someone who's just doing design, someone who's really good at machining, and someone who like is used to like assembling stuff. So a lot of times you're not actually the person who's handling your parts or making it. So it's really important that you're very clear in how you're conveying information in a way that's like really not confusing for them. Depending on how, like a lot of people say, like using GD&T and different like sort of drawing standards is really like a language. Like depending on how you use it, you can communicate a lot more info than just numbers. You can like some people can really interpret things as in terms of function, like what it fits up against, like depending on how you uh, like write notes and stuff. So yeah, it's pretty important that you only including info that's needed to like create your functional part. Some dimensions just don't matter. You'll realize like to someone, depending on like the application. Like if I'm giving someone an assembly drawing, I'm not going to litter the whole thing with dimensions of each part. That can be in its own drawing for the person who's like machining that part, right? The person who's assembling it just gets the parts. They're expecting it to be fine. What they're worried about is like, oh, when I put this in the assembly, like how far away should it be from this part? Like you include the relevant information for whatever the purpose is. Um, so yeah, and like I said, like once you start to understand drawings, it can be a little quicker to gain information for looking at a part for the first time. Um, Especially if you're working with like outsourced vendors. A lot of them like might yeah, they'll ask for like sure a model, but they'll also ask for your drawings. This like sets how they inspect parts, how they make them, everything like that. So some basics of like reading a drawing. Generally you'll see these orthogonal views, like it's arbitrary whether or not they're front view, top view, or right view. But generally, like basic level, you'll see three different views that are all like perpendicular to each other, right? That show all the important features of a part. If you've taken MA 94, which is like sort of the CAD and drawing class, they'll dive into a little bit of this, how like once you start to look at the shapes, depending on like, even though that they're just 2D like drawings with like lines, as you start to get more spatial awareness, like you might not even need this isometric view, which is the more like 3D view, right? You can sort of just interpret like what this part looks like, just from looking at the three views or even just two of them. You can like create the third view and stuff like that. Um, so yeah, you'll see all these views, and these are like dimensions, right? That just sort of indicate like a distance, location, or size, right? And they have these leader lines that sort of point to what it's referring to. So if you look at this 2.4 inch dimension, you'll see that its leader lines go to the edges of the part. So this is just referring to the overall length of the block. This 1.6-inch dimension goes to the center lines of these holes, so it's the hole to hole distance. Um, and like, yeah, hopefully it becomes more intuitive, right? This one points to each of these lines and has like a degree symbol, so that one's the angle between the two lines. Um, and yeah, this is the title block. This is in the bottom right of, or like in one of the corners of any of your drawings. This will change depending on who you're doing the work for, which club you're in. Most clubs will have their own drawing, like template. If you want the BFR template, it's in the box. There's a folder in the main box that says BFR like drawing templates. When you create a part in SolidWorks, I'll show you, it should pop up if you've set your like file directories correctly to automatically pull those templates. So you can just select the BFR template when you're making a drawing. But some simple like information is conveyed here, right? Like you might have an ID number or a name. A lot of times this is auto-filled based on the you can add a bunch of properties in your part files. So it can auto fill in like, oh, I have an ID number instead of just the name. Like this will end up with like a bunch of numbers and stuff. Or it might automatically fill in like your material over here, stuff like that. This is the standard tolerance box. This will pretty much say like if I don't specify a tolerance, and I'll talk a bit about tolerances later. This is what you can refer to in general if there's nothing specified. This refers to like how accurate certain dimensions need to be. We also have this is pretty common like approval checks. Um, this one obviously doesn't have anyone's name on it, but it's important to know like if I'm looking at a drawing and I have no idea what's going on, like knowing who made it, like who checked this off, who might be able to tell me something about like what this part's supposed to be like, or like clarify a bit more if the drawing's like not that good. Um, some other stuff about like what sheet number it is, right? The scale of any of the views. But yeah, some basic terminology. Dimension is like numerical value dictating the size, location, or geometry of a certain part or feature. So I already talked about like how to tell what a dimension's like leader lines are pointing to. If you've heard me throw around the word nominal a bit, if you've never really used that, it's like the design spec or like the normal spec, like what you're ex just think about like what you might set a dimension to in CAD. So like that's what you're expecting it to be, but in real life, it's not going to be that. It's not going to be exactly that. Like maybe it's instead of 2.4 inches, it's 2.405, right? It's still pretty close, but your nominal dimension is like what I was expecting, like the perfect world dimension, right? Um, and tolerance is like your allowable deviation from nominal specifications. Like just think about it, like how off can a part be? And I'll say it's still fine. So some parts like you'll be surprised how far you can get away with a part being off, especially in like racing or like any like student club. You can get away with some like pretty messed up parts and they'll still perform their function just fine. Um, in industry, it's like honestly sometimes surprisingly still similar where a lot of things are maybe like you have a lot more wiggle room than you might think. A good drawing will very clearly show you the limits. Some of them, like you actually have more wiggle room beyond the tolerances of the drawing. Um, like someone might not have done like all the work to set like a certain tolerance correctly. So if it's out, they might say, "Oh, it's still fine." But yeah, so tolerance is like how much error you're willing to accept, right? And if you're reading this in the drawing, you'll see all these plus and minuses. This is one way of indicating tolerances besides those standard ones at the bottom. This is bilateral tolerances, where you have a different number for plus and minus. So for this number, my nominal one is the like original number on the left here. So 1.285 is the nominal dimension. Um, but I'm saying it can like this top tolerance is 0.000, so it can't go larger than 1.285, but on the lower bound it's allowed to go down 15 thou, right? 15 thousandths of an inch. So my actual range, if I looked at this, is 1.270 to 1.285. So when someone machines this clevis for me, they're saying this is good. I'll take it and then I'll inspect it. I'll take a pair of calipers, right? And I'll measure like the thick or the width of the block and say, okay, as long as it's in this range, it's acceptable, right? Um, it's a very easy way to see if like someone will throw out a part or like again, this is like about the quality checks. So if you send this to an outsourced vendor, when I like pay someone to make a part, it's expected to meet the drawing specifications. So hopefully when I get it back, it's actually like all within those dimensions, um, and stuff like that. I mentioned this a little bit earlier. Assembly drawings are also a thing. You'll touch on this a bit. They have varying complexity. This is our chassis assembly drawing that we need to make and send out to our outsourced vendor. Um, so this can specify how parts come together, some assembly level like dimensions and other important info. You might have heard me throw around like the use of a BOM or a bill of materials. This specifies like all of the parts and materials that are used inside of an assembly, right? So we count every part, every bolt, every like piece of hardware that's in something. This one counts like every single tube that makes up our chassis, including like its quantity and its different lengths and thicknesses. So yeah, there's a lot of tubes on the chassis, so this gets like really cluttered. And then you can use these are called balloons. You can see over here, it's a little small, but these are item numbers, right? Like line numbers for each tube. And then these balloons come with like when you click on when you have it referenced like this tube right here, it'll automatically pull what part that is and reference the BOM. So this tube is like line 27. So if I'm the manufacturer, I can look at line 27 and it'll tell me which tube to use there. Um, so yeah, obviously this is a bit of a messy one. That might be hard to read. But assembly drawings, you could do a lot of stuff with that. I'm not going to go as much into it. Um, yeah, so a bit about GD&T. This is a bit more of like complex drawing stuff. They don't teach it in MA 94, but it's a very common skill that you'll see this on like a lot of job applications. They'll say preferred skills like use of GD&T, and if you say you have this, they will probably ask you in an interview. Um, yeah. So it's good to like really know your stuff when it comes to this. And being good at like using GD&T and understanding it will really give you an advantage in certain areas of industry. What is it? It stands for geometric dimensioning and tolerancing. And it's basically like it's like its own language to sort of minimally constrain how a part is manufactured, right? With the goal of maintaining functional requirements, right? And functional requirements, I'll use that word a lot. Um, but the whole idea is like if I say your part has to do this, right? Like the wheel has to roll, right? My functional requirement is once I like finish this wheel, like and this tire, it needs to be able to roll. If I build you like a square, it might not meet those functional requirements, right? So having a really good understanding of your design criteria and the functional requirements of any part you're making is really important, because it allows you to sort of set the bounds of like what you'll accept as a part, right? Anyone working in like any of our structural sub teams will know you do like your FEA or all your different like structural hand calcs to verify that a part like won't fail. That's a functional requirement, right? Our parts, like their function is withstanding the loads that are going through the car as you're like making a corner, right? So if it fails FEA, then it's not meeting that functional requirement. Um, and that same sort of logic can then be transferred into how you make your drawings and how you set tolerances. I'll talk a bit more about that later. Um, but yeah, GD&T more accurately controls like the inspection and acceptance of parts. It's a lot more complex of how it like what it's actually checking for in a part. Um, with the basic dimensions you saw on the other drawing is very clear. Like this is just the thickness of the part or the distance that I can measure easily with a ruler or calipers. Um, but certain features that aren't as boxy, right? Like if you look at an airfoil, right? Like it's maybe less clear about oh, if I'm asking for a certain dimension, how am I actually gonna like measure that? Maybe I can do like the thickness of like the max points, right? Where the calipers will clip onto something, but like that might not be useful information. So you need to find other ways of really defining what's like actually an acceptable part outside of just like linear dimensions. Um, but it's important to like really understand it because there is a thing as too much GD&T, right? Like I said, there sometimes you have a lot more wiggle room than you think for certain parts. But if you're really constraining like how much they can do, if I'm saying it has to be exactly like it is in CAD, if you're off by more than like 1,000th of an inch in any dimension, I won't accept the part. That's going to cost a lot of money because they're not going to get it right every time, which means they have to throw it out, start again, right? They're going to have to do this a lot. The more and more accurate you need a part to be, the more expensive it might become. So it's important to know the limits of like what is too much or like what like this is just enough accuracy. There's a couple of things on here when I post the slides, you can like click on the links. There's some good resources online about learning about specific symbols and stuff. There's some ASME like global standards for GD&T usage that you can look at. It's a pretty lengthy book. We have it in the drive. There are some weaknesses to it, and you'll see why we don't actually use this for a lot of our parts, especially in-house. It's pretty useless if you can't adequately measure it. Um, so for us, calipers are pretty like easy to use. Like I can just like measure the distance of something, right? Those are easy dimensions for us to check, right? Or something I can check with a ruler. Like that's useful, right? But if I ask you to like do some complex analysis of like the form, like the roughness of a surface, and I can't, and I don't have the tools to do that, it doesn't mean anything that it's been put on the drawing, right? It's just something I can't check. Um, so that's something to keep in mind. Um, we're slowly evolving our inspecting like skills and like what we're able to do at BFR, but there's always limits. So just keep that in mind when you're making in-house parts. But you'll see this a lot more for like our CNC parts that are going outsourced. Um, Datums and constraining a part. Constraining a part, like I mentioned it earlier about degrees of freedom. Um, there's 6 total degrees of freedom or ways a part can move. There's 3 translational ones, right? There's your 3 axes that you can move a part around on, your X, Y, and Z. And then each of those can also be an axis of rotation, right? Like I can rotate about any one of those axes. So the goal is when I'm like inspecting a part or like I'm like setting dimensions, I like want to constrain it a certain amount, right? So how many points would you actually, it's a good like sort of like mental exercise to see how many points would you actually need to fully constrain a part. And the answer is 6. So you can see on this little block here, um, with any part, this can be applied. So if I have 3 points, like that makes a plane. And if we say, like, take my phone, for example, and I set this whiteboard as the plane, right? Once I place it on the plane, it's removed 3 degrees of freedom because it can't, like, once I say it's stuck to here, it can't move in and out, right? It's like I can't push it through the whiteboard. I guess I could pull it off, but like, we're just going to say it's stuck there. And then it also can't rotate in 2 directions, right? I can't rotate it like this because then something will lift off the whiteboard. Same thing with this direction. I can't rotate it this way, but I can still like scooch it wherever I want on this plane, and I can rotate it around. So we've fully constrained 3 degrees of freedom with this, but there's still 3 remaining. The next thing is you take 2 points, that makes a line, right? You'll see the green dots on that block. If I put like an expo marker here, this is my line, and I say this has to be butted up against here. I've removed another 2 because now it can't move like this way, or it can't move through the expo marker. And it also can't rotate in this direction now, right? Because then like part of it would lift off the marker. So now there's only one more like constraint I need, like it can move up and down. So that's where the last point comes in. You take 1 point and I say butt it up against my finger. Now I can't do anything to it, right? It can't rotate in any direction, can't translate around. So that's fully constrained. Um, yeah, that's just a good exercise to have. This also applies to when you're making your CAD and your assemblies, how you're thinking about when a part is actually fully constrained or fully defined, as SolidWorks is. So what do we actually like? How do we actually represent these constraints? And that's through what we call datums. So datums are references used to like sort of locate or orient different features. And you can sort of choose on a part like what datums you use. Right. So for my phone, I decided to choose this front face as one of my datums that actually sits on the plane. That's the plane that's defined. I chose this edge as like my second datum that butts up against the marker. And then there's a certain point on here that I defined as what I'd butt up against my finger, right? So that's a good way of thinking about what datums are. It can get pretty complex. In terms of like what you'll see on a drawing, you'll see this little leader line with an arrow coming out to a box that just has a letter on it. So this is datum A, and this refers to the surface of the part. Again, you can look at like online resources and stuff to get a better idea of when you see like a datum feature on a drawing, what it's actually meaning. But yeah, this just means that this whole face is a datum. Order actually does kind of matter in your when you're making these datums. So oftentimes the first one is considered that plane, right? And then so and so. So generally you'll order it in that sort of like constraining order. You can do it off of surfaces of surface features or off of center lines or center planes of features of size. I'll talk about what that is in a sec. The first datum, like I said, is often the plane, second's the line, and then the last one's your point. But there's different combinations, especially if you think about like this one, it's second its second one is actually the center line of um the cylinder here, right? Like the bore here. So if I put like I have a hole right in a part and I plug that and I put a pin in that hole, that actually constrains both my X and Y directions, right? Because like once I put a pin in it, it can't move around, but it can still rotate. So depending on what kinds of datums you use to control your parts, you'll actually like constrain them in a different order than like the simple like 3, 2, 1 concept, which is the plane, line, and point. Um, so yeah, but datums can you can go down quite a rabbit hole of what the best kind of features are for your datums. Um, again, you can ask me for more info later, but yeah, that's the basics of it. Features. So there's two kinds of features that you'll refer to when with GD&T. There's surface features and features of size. So a surface feature is like a surface of a part, right? Like you can't exactly define it. It can get a little funky when you're like trying to think about what differentiates the two. But a surface feature is something you really can't like apply a certain dimension to, right? So if I show you this green surface, right? Is there like a number that would like represent it? I guess there's area, but yeah. So I guess you can, but not in terms of like distance and stuff. So this is where like stuff like features of size come in. So there's two examples here. There's a slot as well as a hole. Um, so anything that can have like an associated dimension with it, like a linear dimension or something, that can be measured with two opposing points. That's the main thing. That's why area wouldn't fit. So hole, slot, or a wall without count. While this green thing is a surface feature, if I took the distance from like this wall to this outer wall, that's now a feature of size. So you can sort of see like anything you can really apply a dimension to might be like, oh, oops, skipped ahead. Feature of size. A hole has like you can position it around, and it also has its diameter, which makes it's the most common like feature of size that you'll see GD&T used for. Um, but yeah, that's just what I mean if I refer to features of size. So there's a bunch of symbols here, and like you'll slowly get a feel. I'll intro briefly each one of these later. There's a couple different categories for symbols in terms of what they control, right? There's the form of something, um, right? Sort of like the shape or like, like the form of any feature. There's the orientation, right? Like which way it's angled or whatnot. That one spoiler is angularity. There's location. This is true position right here. Like where something is actually located. Um, Run out is sort of its own thing. It's a bit of a form thing, but run out is sort of like if you have a shaft how concentric it stays pretty much, or at some point, like while it's rotating, it starts to bow out or something like that. I have an example about that later. And profile, which I'll talk about a bit more, but that's pretty much like it can do everything. Um, these are feature control frames. This is what you'll actually see in a drawing that sort of specifies how you're like using it. There's a lot of info on here and it can get pretty confusing. So this is for a hole, right? This hole has its own like normal dimensioning, which has its diameter. So it's a 5/8 inch hole with a standard tolerance of plus or minus 0.005 or 5 thou. Um, and these orange boxes just only refer to a feature of size. Um, and then this is actually our feature control frame here, this box here. I'll show you how to make that in SolidWorks. But the first box is the geometric characteristic. This is where you'll pull up one of these symbols from before of what you're actually controlling, right? So here we have the location symbol. Oh, oops. Here, like we're controlling the location or true position of our hole. Um, Next is our tolerance that's actually applied to said control. So here we're using a 30 thou control. Um, there's also this diameter size sign. You have some with it, some without. This just sort of refers to different. Yeah, what's up?
What's the difference between tolerance above of 5 thou versus the 30 thou?
Yeah. So so this top line is just referring to the size of the hole, right? So it can range from a diameter of 0.62 to 0.63, right? And that all be acceptable. Um, if you have like varying drill bit sizes or whatnot, they'll be a little bit off. So I'll accept all of that. This is now referring to like the other control or the position of its axis. Um, you can have modifiers. This is for like features of size. I'll have it has its own slide later. But this sort of like adds another layer of like what the tolerance zone actually means, depending on like the size of something. But I'll talk about that in a bit. And then the datums at the end, this is like which ones you're referring to. You can have like generally up to three. But you can have less as well. So sometimes like you don't need to fully constrain a part, or you don't want to fully constrain a part when you're setting a dimension. Sometimes like certain things like the flatness of an object might not, like if I'm looking at the flatness of this face, it doesn't really care about like whether or not it's like moving around in space, right? It kind of only cares which plane you're referring to, like when you're measuring the flatness. So if I'm like measuring a probe across this face to see how flat it is, I kind of only need to stick it against this face, which would be datum A, right? So you'll see, I think, some examples later of flatness being used. Oftentimes it's just one datum where like I only need to constrain it like this, and I'll measure across whether or not it's moving around or rotating. Doesn't really matter. Um, so you can have like less than three datums if you want. It gets really funky if you're using like stuff like true position. You can do a lot of cool stuff with using less datums to give yourself more room for certain things. But uh, yeah, that's for another talk. So first one is flatness. Like I said, you can even have like no datum on it. This controls the form of a surface feature between two parallel planes. You'll see this, you'll see this pop up a lot of like what GD&T is actually referring to is if you have like your nominal, like your imaginary like nominal surface of like the ideal surface of the part, right? Ideally it sits like here in space, but when I say a certain flatness, it's not actually measuring like it's not actually like looking at it like each particle is like this flat, right? Like what it's actually doing is just saying, okay, I have two other planes that if any point along this surface goes out of bounds, now I'm saying it's like not flat, right? So a good way to think about it is let's say I have this huge field that's right next to a mountain. Like the field you would say is flat, right? But if I expand my search to the whole area, yes, well, it'll say like this whole area is flat because at one point it tells you that there's a point that goes out of the like bounds. It'll say it fails the flatness check, right? So this is an example of why it might be important to understand like how they're actually measuring things. I like for example, at work, I got a report back that like there were a bunch of dimensions that are out of tolerance on a part. And I just see, oh, this one fails. Like it was a profile check, but essentially we're pretty sure it was a flatness issue. But you can remeasure certain things if you have an idea of what might be going on. We were pretty sure that there was just like some random point that was sticking out, or it was too deep or something. Just like some random chip that might have been affecting it. Which in that case, the majority of the surface is flat, and therefore you can use it. So we went back, checked it. It was actually still flat. So it's important to understand like what it actually means when it says something's out of tolerance for flatness, right? Um, so yeah, if I say 30 thou tolerance on my flatness call out, it'll go up 15 thou and down 15 thou from like your nominal space. And you can see like if you like really zoomed in on a surface like to like the particle scale, right? It looks really rough, right? But this is still flat as long as all its points are sitting within that like good zone. Um, so yeah, cylindricity is the exact same thing, just around a circle. So like even though you might say that this thing is not a circle, um, it is by the bounds of like GD&T because it'll just create two concentric cylinders that are zero point 0.03 apart. And it'll just say, as long as no part of your cylinder goes outside of this line, you're good. Um, it's like it's close enough to a circle, right? So same sort of thing. It's controls the form of an object. like how much it looks like a circle, kind of. Yeah, it's called angularity is the next one. Again, you'll see the trend of like you can always see like the sort of multiple planes that they're creating that create like a keep-in zone, right? That makes it very clear whether or not something's failing. This angularity controls the orientation of a surface feature between two parallel planes relative to a datum. So if I have my datum like a flat face on here. There's an extension of angularity, which is perpendicularity, which is basically just angularity at 90 degrees, right? So if I want to say I really want this top surface of my phone to be like perpendicular to this face, what it'll do is like this datum, right, is datum A, and then I'll say I want it perpendicular to that. So it'll create a plane now that's like perfectly like imaginary, like 90 degrees off of that datum. Um, and then it'll create a zone from there, right? That's are we still using 30 thou? Yeah. That's 30 thou apart between your two planes. And like as long as like it's sitting, right? If it's out, like part of it will stick out of the box, so it won't count. Um, so yeah, same sort of like measuring scheme for angularity. Um, and you'll see that like depending on how you're using it or what you're using it on, it might apply to different things. So that example was doing it to a surface feature, right? Like I want this surface to be a certain like angle from a datum. But if I apply it to a feature of size, right? Like a slot or commonly like a hole, I might say like this one uses a perpendicularity control on a hole or like a bolt or whatever this is. Um, and that'll basically say it's applying it to the axis. So the axis can only be so angled before it actually goes out of bounds. Um, so you can see like if I'm asking for this to be perpendicular, right? This cylinder, if I take like this is my like imaginary axis of my like bolt or whatever sticking out, right? I'll create a 0. Uh, for this one, it's saying 0.2 is the tolerance. And it should be it's a what's it called? Um, it's a circular like tolerance zone because it's got this diameter symbol here. Um, so it makes a cylinder around it. Otherwise, it'd make a box. But it makes a 0.2 inch tolerance cylinder where if the axis of this piece ever goes out of that box, then it now fails perpendicularity. The hole is not like straight enough or whatnot, right? Um, so yeah, they're like again, depending on how you use these features, they can mean a lot of different things. That's why it's like a super huge rabbit hole. Um, and like can always learn more about how people are using it. Um, like yeah, depending on who you're working with, some people have a very consistent style, or you meet someone new and you're like, I don't know what this drawing means. So yeah, position is probably like in my experience the most used one besides profile or like where it controls the location of a feature of size. So obviously like if you say the position of a hole, it's pretty I think it's pretty clear to think about what that means, right? You're controlling like, oh, where do I place this hole, right? And oftentimes you're doing it with at least 2 to 3 datums. But funny enough, like it also controls the orientation of a part. So something like this is actually a problem that's popping up with the drivetrain drawings for our chassis. If you guys know, this is a bit of an example. Um, so you can control, we're already controlling the position of those holes, but it was requested that we also control the perpendicularity, right? So now it's a question of is the perpendicularity control overkill or is the position just enough? Because if you look at it, right, the way it measures position is it'll create a tolerance zone around the like theoretical axis of a hole, right? And as long as your axis stays within this bound, right, like it's good. But you can see here with this red line that this will also, it's like similar to how that perpendicularity control worked, where if it's too angled, it will still fail position. So Like you can have a hole that's like centered in the correct spot, but if it goes out to the side, then it's failing your position control. So position is really powerful. You can use it to control like perpendicularity as well, or like the orientation of a feature of size. Here, you can see it for something that's non-circular. This is like the difference between the two tolerance zones. So if you add the diameter symbol, right, it'll make a cylinder around it. Otherwise, it just does back to your like linear like dimensions, right? So for a slot, if I do the position of the slot, it'll measure the two sides of the slot or the feature, and then it'll average out to find the midplane, right? And if that midplane goes out of bounds at any point, then um that's how like its position is measured. Same thing again, if your slot is at an angle, it might go out. So it controls that as well. Um, oh, and a good thing for order, the first datum is should be perpendicular to the axis. So, right, if I'm drilling a hole in my phone, um, I'm gonna say like it's always going in like normal to it. So the first one is always the plane that it should be resting on, right, when I drill the hole. And then the reason why you can do less than three, right? Like maybe you're less concerned about it moving in like certain directions. So I can like loosen tolerances in certain areas if I don't include some datums. But that's a little bit more advanced than you need to know. Um, but yeah, so here's an example of what the like diameter like tolerances do versus like normal. Um, so if you like use a circular like tolerance zone, this is what you'll see, right? And just some notation stuff. If you see a box dimension, that's called a basic dimension, and that means it's just for reference. Like this is just telling you like where the hole is, but this like is just to tell you like where the hole is for the GD&T stuff. Um, it's got no associated tolerance with it unless you're looking at like this box here, right? So this is just reference. Like um the G when you're doing GD&T, it doesn't actually matter like what those say. That's just like for like a human to interpret or like read out how far away is it supposed to be. But this will always take the actual just true position. It doesn't matter if like this one's a little off or whatnot. It like or sometimes you'll see with normal dimensioning, if you daisy chain dimensions, you might get like some stacked error. If like this hole is a little off, which now means it's further away from this other hole. Um, but yeah. So if I do this, it makes this circular zone, right, in which my axis can like is allowed to move, right? And let's say I'm trying to fit this up against another plate that has a bunch of holes in it, right? I need to make sure that these holes overlap. But like with different diameters, like maybe there's a little bit of wiggle room before like my secondary hole that I'm trying to control is no longer fully overlapping with the other one, right? And that would be failing its functional requirement, right? My bolt no longer passes through the hole. So so you'll set your tolerance, right? Right now it's zero point 0.1 to whatever like that bounding condition is. So like I'll say like if it goes any farther out than this, then it's likely like it won't go through the hole anymore. That's how I set the tolerance. But here you'll see I use a standard dimensioning approach. I say it's 15, it's probably millimeters. Um, 15 millimeters off from any direction with zero point 0.1 off, right? And you think it's the same, right? It's zero point 0.1 of a tolerance on all of its dimensions, but the tolerance zone it actually creates is a square, right? Um, but like something about squares, right, is not all of its points around the perimeter are equidistant from the center. So a circle, if I go to any point, if I put the axis on any point of this circle, it'll be the same distance away from nominal, right? But if I do the same thing with the square, right, like it's zero point 0.1 inches off if I go this way, right? Like if it's like off in the vertical direction by zero point 0.1 inches, it's zero point 0.1 inches off from nominal. But if I'm also off in the like in the lateral direction, now I end up in this corner, right? Which is actually like farther away, which might be too much, right? So now I'm accepting parts that otherwise I'd say like I don't want that. It's too like the hole is too far off, but it allows for some more room. Oh, yeah. So right? Like here, if I use if I use the square like dimensioning, this hole out here might be too far out, and I'm accepting bad parts now, right? Where now I get it back from the manufacturer, there's nothing wrong with it, but now I put it to assemble and it won't go through. And like I can't blame the other guy because he did it to my drawing specifications. Um, so now to compensate, I'll decrease the size of the hole, right? So now it's 0.07 tolerance on all of these. So the farthest out it goes, like this point out in the corner, is now um, like on the same is zero point 0.1 inches away from the center, right? But now I'm throwing out good parts because the edges of the square are now closer than they were before. So like something, so um, especially with holes, like you might see that if you use like the circular tolerance zones, it gives you a lot more accurate of an idea of like what's acceptable and what's not. Um, so yeah, this example where you make it smaller to compensate rejects good parts and is really tight. This one is maybe accepting parts that aren't usable. So keep going. MMC and LMC, these are those modifiers. So this M symbol right here, right? What they stand for is the max material condition and the least material condition. Um, and these are like bonus tolerances that sort of allow for like easier manufacturing while like keeping the functionality in mind. Um, so like if you have no modifier, you just keep going as normal. But if you have the modifier, you have to think about some of your tolerances on the feature of size, right? So if I have a hole, the max material condition refers to like I have the most material, so the hole is as small as possible. So if the hole is like 10 inches or 10 millimeters wide, right? And it has a 0.5 millimeter plus or minus. Now I'm saying it's 9.5 millimeters, right? Um, and this is what the standard one, it like if you don't include a modifier, it'll just say no matter what the diameter of the hole is, I don't care, your tolerance is the same, right? Which maybe that's fine. And like maybe you can hit that. But if you think about it, right, when I'm trying to fit my two plates together, um, if my bolt is smaller or my hole is larger, then I have a lot more wiggle room, right? Like I can be farther off and still like the parts will still mate together. So that's sort of like the idea of this is that with a bigger hole, like you have more of a tolerance zone. So with the least material condition, right, which in this case is the largest hole possible, so 10.5 millimeters, you get an extra zero point 0.1 millimeters of tolerance with the modifier, um, because you add on whatever, like my bolt got smaller, so I can add on like half half of the diameter in either direction. Um, so what's it called? If it's now like a normal size, it's 0.6. Like you see across the board, it gives me more tolerance room than only if I have the max material condition or the hole is as small as possible, that's when I actually have my tightest tolerance. So it's zero point 0.1 if I have the tightest possible hole, but for every millimeter that your hole gets bigger, I'll give you more room to mess up, right? So it accepts more parts based on functionality, right? That's a pretty useful one. Um, Profile of the surface is the most powerful control. It controls everything. It controls the form, orientation, and location of a feature. Um, like now I have like a curved plane or some like fancy feature, and I say, hey, like control this with a profile tolerance. It now creates two planes that actually just follow the whole curvature and everything of that part, 0.03 inches apart at any point. And again, same thing. If any of those points falls outside, then it'll come back as like out of tolerance. This is a good example for things like a lot of carbon fiber work, right? For any like planes or like any of our aero package components. This might be something where like at an industry level, you're using profile tolerances. Um, and I'm saying like, hey, I like need it just to follow this shape well, right? Maybe that's what I'm asking for. Let's see, do I have another thing on it? Um, yeah, and profile, it's like it's pretty flexible where if you don't include any datums, it only controls the form of the service because it has nothing else to reference it against, right? You can't control location without a datum because I can't tell you the absolute position of something if my part is allowed to move around, right? It's allowed to move around completely. So the only thing I could do is say on the surface, it's this flat, right? So that's why these two are the same thing. If I don't refer to a datum, it's basically a flatness dimension. Um, and then when a datum is referenced, you can control everything with it. Um, so yeah, this one, you'll actually see that on some of the drawings, I'll pull it up later, that the drawings will, a pretty common thing is you'll say, like overall, there's a total like profile tolerance of like a pretty loose number, but there you just throw that in there. So like for say some of our drawings, right, where we add a bunch of complex weight cuts on the part, I don't actually need them to measure that, right? They'll only have to inspect what's actually like said on the like whatever the drawing says is what you have to follow. So if I don't add every single dimension to like some random weight cut, right? They could give me a solid block and say that meets the drawing, right? You didn't specify it. Most of our sponsors are pretty nice and they know what we want. So even if we give them shitty drawings, they'll accept it. Um, but they could, if you didn't specify any dimensions regarding those cutouts, they don't have to include them, and that would match your drawing specifications. Um, so we throw in just a general, like standard, like if nothing else, like it should be like within a certain like profile tolerance of the CAD, and that just saves you some headache. Um, Total runout, I mentioned this a little earlier. They basically control like the form across the length of a surface. So if I have a long cylinder, right, it references the center line of said shaft, and just make sure that at no point it's really like straying super far away from the axis. If you have like a bend in your shaft, right, it's not gonna run as well if you think of any like motor or like transmission components. Um, Runout can cause high vibration, high stress, and fatigue in rotating components. Um, so yeah. Modifiers, oops, we already covered that. So yeah. Engineering fits, won't go too much into this. This is just like a naming convention for different fits you can use. So clearance fits is basically like something will slide in super easily. There's no issue. Transition fits is where you're starting to get close, where you might have a little bit of resistance. And then interference fits, you might actually have to do a press fit. We're using like the hydraulic press to actually like force two parts to mate. This is like common for any bearings, right? Our uprights have bearings that we need to press in. And if you mess up those fits, it might not sit in how you like it. It might be too loose, right? So if I refer to something as like F7 or something, it refers to a certain tolerance based on the nominal line. Like this line here um is like what I say in CAD, right? And in CAD, the hole is just the same size as like the bearing's outer diameter. But in reality, um like on a very small scale, how I change like where on the line these parts actually end up will determine the fit. So, right, if the outer housing, right, or the upright is actually smaller by a bit, you're gonna have more interference when you're pushing in a bearing, right? So, yeah, there's two different bases for these, hole basis and shaft basis. Hole basis is where you have a constant hole and you're changing the size of your shaft. So if you have an off-the-shelf part that you know the diameter of, and I'm trying to fit like this is like if I was choosing a bearing, right? And I know the hole size I'm going into exactly, and I say, okay, I want this to have like a little bit of a press fit. I'll choose like a C blank. That's not correct, but or let's see. I'll do a um, down here. I'll do like a J6 transition fit, right? And it's lowercase, so you know it's whole basis versus these ones are uppercase. Um, so so yeah, and then same thing for the shaft, but the opposite. Um, Okay, so application, like with all these tools, like you can use the control features to really control like the functional requirements of your parts, right? So an example, is, and you should be specific when you're thinking about what you actually need to limit, right? Not everything needs to be controlled. Not everything is like matters that much. Like some things just aren't that deep, if you mess it up. But some phases are really critical, and it's important to know when you really sharpen your accuracy. Um, and you can drive up costs a lot if you're being over constrained. So for an example, the hub has to fit through two bearings on the upright and spin. Like what sort of controls could you apply to the hub to improve performance and its like functionality? Anyone have an answer based on some of the ones we've talked about? So yeah, it's a rotating shaft.
The rotating shaft, it would be kind of like electricity, but it's when it's run out.
Yeah.
Make sure
Yeah, exactly. You have it exactly right. So you can see how much I rushed through these parts of the slides. So yeah, this is the hub. We actually do apply a runout control to it. And you can, yeah, you're exactly right. This is a bit exaggerated, but pretty much if you have too much runout, right, you're gonna both interfere with the bearings and it might not actually fit through when you're trying to assemble. But also you're gonna increase your wear, like your fatigue life goes down. Overall you're like straining your parts a lot, right? Because they're too eccentric from each other. Um, there's maybe you'll see if you scroll up a lot in the Slack, but we put our steering column on a lathe to check for its run out. That thing was wobbling all over the place, and we're like, well, this is like terrible. Um, so, so yeah. How do you set tolerances? That's a good question. I mean, anywhere you go, honestly, there's like a lot of examples of where tolerances are set very poorly. Um, like half of my job this summer was like, hey, this part is out of tolerance, but I still need to see if it's okay because it seems like they set the tolerance very arbitrarily, right? I'm like, I don't see anything that's actually dictating this, but they put a super tight tolerance on it for some reason, and I just want to confirm like the part is still going to be usable. So you can do something called like virtual conditioning, which is where you almost take the worst conditions based on tolerances, um, and see what happens. Like when does the part actually fail? So some examples, right? We talked about like how far off can a hole's position be before a bolt no longer will pass through. That's a great example of like that's actually what's like driving your tolerance. If you go out of this, like it's not going to fit. Um, or like there's no guarantee that it fits. And you can do this whole thing of like what percentage failure you might have. Um, but that's one thing. Some things are also structural, right? If I have like a cutout that's a slot and it ends up being too large, right? Like now I have a wall nearby that's thinner, and it's a highly loaded part. And now I'm not sure like how much it affects my margins of safety, right, with my FEA. So sometimes something that's done with FEA is you can actually design in based on like your worst conditions or your least material conditions, where like the part will like least material conditions is often you're thinking about failure of like structurally, right? There's the least material there supporting you. Most material condition is often for fitment of like bolts and stuff. Um, so those are some things you can think about, like yeah, how thin can this wall get before the FEA fails, and I can actually run my FEA at like a thinner wall thickness to see like where how much room I have. Um, or you just use standard tolerances. Right? There's that box that we looked at before. Depending on how many decimal places you apply, will set your tolerance for anything that you don't feel like specifying. These are sometimes pretty arbitrary. You're just like, I don't want it to be too far out. I'll put three decimal places. Oftentimes we're a little lazy on this team and we just always do three decimal places, which is a little bad. But but yeah. But if like I don't really care that much. Like the overall length doesn't affect anything. I'll do like one decimal place and then it's uh plus or minus zero point 0.1 inches, which is a lot when you're machining. That's a lot of room. So so yeah. Um let's see. I'll go into a bit of mhm. Yeah, so for SolidWorks, right, I'm gonna go bare bones. So we'll start with like just generally for your guys' application on the team. If I create a new document, this is like what at least what I see, the way I've set up my, if you go to settings and then you go to file or default templates, you can set where it takes templates from. So I have it take it from that folder and box to automatically get them. Um, this way it doesn't just give me the blank ones when I ask for it. So I'll like we have two different sizes. A is like the standard printer paper size. So let's do that. And yeah, you'll see here my first note is unless otherwise specified, this is the profile thing. That sort of like gets you out of any like big errors where they just don't include features. So they have 10,000 of profile, which is maybe a little tight. Um, but so they generally have to follow the CAD. Like they can't be off by more than 10,000, pretty much. Um, yeah, so you can see like you have your notes up here, like stuff you might have to do. For anything that's like yeah, you can just say like, hey, if I didn't include a dimension, just look at the CAD, right? But I'll choose whatever part I want. We'll just do a clevis. So this is like a Mark 10 part. Let me do this one. And once I select it, right, I can place it somewhere. And this is where I'm adding like those orthogonal views. Um, and automatically it'll try and make my like 90-degree views from there. So I could just keep clicking, get my right view, get my top view. And then if I go like off to the corner, it'll do my isometric view. Right. And when you click on one of these, when you click on any view, this page over here is how you'll change some of their properties. So oftentimes for the isometric, we'll fill it in, make it a little clear. Everything else is just lines, no fill, just to prevent any like confusion there. Um, in annotation, the new SolidWorks is weird where you have to add a lot of the tabs from before, but I like to go into annotation. I can add smart dimension, which from your part modeling, right, is how you set dimensions. But here in drawings, you can't actually change anything. So here you're just like, this is how I grab a dimension. So it's the same system as in the other one, right? And then I'll place it. And then it doesn't ask me to change it, right? Because I can't. It's just whatever the CAD specifies it as. Um, and then if I click on the dimension itself, you can start adding other stuff. Like it's not originally dropped down, but you can do like tolerance and stuff. So right now it's set to none. If I want to set a dimension for GD&T, I'll do basic, right? I can set here. This is where I control how many decimal places I go to. I can do bilateral, which is the one you saw on the example drawing earlier. And I'll just say like, you can go 0.01. And then this one can be minus 0.05, something like that. Um, right. And then I'll click OK. This is how now I've added a tolerance that goes beyond just the very basic dimensions you're adding. Again, if I just add a dimension without saying anything, it'll refer to like this one's to 2 decimal places. So now it's just inherently a 0.01 plus or minus tolerance zone. What are some other things I can add? There's datum features. This is all your GD&T stuff, right? Datum targets is a bit different. That's like if you add specific features that you want someone to reference when they're like constraining a part. Um, that's a little more advanced. Generally, probably won't need to use it. So for A, I want this bottom face, right? That it sits on, right? Like sometimes you could just go based on gut feeling of what your datums are going to be. And I'll place that there. B, let's see, maybe I want this sidewall, right? A line. And then what should my last wall be? Like maybe this one's another one. And now I've set all my datums. I can apply them now. I'll click geometric tolerance and then I'll attach it to another dimension. So we'll attach it to this guy, the 1.24. I don't And then if I double click on the box itself, uh, now this will pop up. And here it's a little hard to see, but this is where I'll indicate the type of control I want to use, right? So for this, like maybe let's go with, you'll see a lot of other symbols in here. Some of them are 2D based ones. Uh, what am I looking for? Maybe I'm looking for, let's just do like, I want a profile tolerance. And now I can start adding all my other stuff sequentially. I can add um, my actual tolerance. I can say whether or not I want it to be cylindrical, right? By removing this or turn it back to square. And then I can choose to add some datums. And then that's done. And now I have that guy. Um, so yeah. Anything else that you guys might want to know regarding how to make a drawing? That just gives you the basic tools where you can find stuff. You can add notes, right? If I say mm, for 0.25 inch holes, use an O drill bit. I don't think that's the correct size, but like you can specify stuff like that. Ah, right. And like again, you can add notes for anything that might help like whoever's manufacturing this. Like, oh, if it's like if your materials are very sensitive to environment, maybe you say like some storage stuff regarding the material, or do not work on this if humidity of the room is like this level. Right? Certain materials are um, very temperamental about that sort of stuff. So yeah, you can see like any sort of control in these documents. It's really up to you how you want to use it and what you want to communicate to people. Um, oh yeah, but if you want to edit like stuff like your name in here, um, you can just add your own note, or you just right click, edit sheet format, and then within the sheet format, you can actually edit these boxes. So this is Colin Choy. I'm gonna scooch that over. All right, and then same thing as a sketch. I'll just exit out there. And then boom, I have this. Once I have everything dimensioned, save as, and I'll just like, make it a PDF, print it out, send it to someone. Um, whatever. But any other questions right that? Otherwise, that's all I got. So stop.